Let's solve some regression problems. The very first problem has this statement. The HRD manager of a company wants to find a measure which he can use to fix the monthly income of persons applying for the job in the production department. As an experimental project, he collected data of 7 persons from the department, referring to years of services and their monthly income. So we have that data which where X denotes the number of years of service and Y denotes in rupees thousands the monthly income. So if you see that a person has 11 years of experience and he has a monthly income of 10,000 rupees, and the other data points are likely so. We are asked to find the regression equation of income on years of service. So if I look carefully, income is represented by Y and years of service is represented by X. So we want the regression equation of Y on X. That we'll find out in a moment. The second question it's asking is, what initial start would you recommend for a person applying for the job after having served in similar capacity in another company for 13 years? This is just a convoluted way of saying that what would be Y when X is 13, because years of experience is denoted by X. So when X is 13, they are just asking for what the salary would be. And so when X is 13, we just have to see what Y is. And that we'll be able to find once we have the regression equation of Y on X, because if we have the regression equation of Y on X, then Y is a function of X. So if we put X is equals to 13 in that, we'll get what Y is, and that's what we have actually done over here. We have the same information that is given in the table in this spreadsheet where we have 7 quantities. So n is equals to 1, 2, 3, 4, 5, 6, 7, and the corresponding X and Y values are like so, likely here. And yeah, the very first the very first step that we have to find the regression equation of Y and X is we find the square of each X value. So if we have a 11, so its square is 121. We have a 7 and its square is 49, and that's what we do for all of the 7 entries. So if we have these 7 entries, then their squares are these 7 entries. And the next thing that we want to calculate is the product of X and Y. So if we have X is equals to 11 and Y is equals to 10, we have the product 110, and similarly for other quantities as well. So we do that for all the 7 quantities. And then our aim is to find the average of these 4 quantities. So to find the average, what we do is we first find the sum, definitely, and then we calculate the average. It's nothing but the sum divided by the number of quantities, that is 7 in this case. So if you find the sum divided by 7, you will get these averages. After we are done with finding the averages, we can find the variance of X, because remember that our variable is X in this case, and this is the independent variable, Y is the dependent variable. So if you find the variance of X, it is nothing but you can even see the formula here. It is nothing but, if I click over it, it is this X squared, the average of X squared, that is the average of the squares minus the square of the averages. So if you have a 68 minus the square of 8, that is 68 minus 64, you get a variance of 4. So you have a variance of X which is equal to 4. Covariance of between X and Y is nothing but, if you see here, it's nothing but the average of the product, that is 67, minus the product of the individual averages. So you have 67 minus 8 into 8, that's 67 minus 64, that is the result is 3. So the covariance between X and Y is 3. Next, we can find the regression coefficient, that is B Yx. I've denoted it with the subscript Yx. This is how we denote subscript, it's just for notation. It is nothing but the ratio of the covariance and the variance. So if you have 3 divided by 4, what you get is 0.75, or 3 by 4, 3 quarters basically. So we have found part of the answer. The regression coefficient B Yx is 0.75. And once we have that, we can use the average X and Y to find the constant or the intercept value, because we know that the average point should lie on the regression equation, and this regression coefficient is nothing but the slope of the line. So if we have a point and the slope, we can find the whole equation, and the constant A comes out to be 2. So yeah, we have the regression equation. It is nothing but Y is equals to A, which is 2, plus B into X, where B is 0.75. So this is the regression coefficient, regression equation of the line. And we had X is equals to 13. So if X is equals to 13, I have a sample X of 13. If I put the value of x is equals to 13 in this equation, what I get is 2 plus 3 quarters of 13 is the predicted y value comes out to be 11.75. So if you have someone who has 13 years of experience, then that person can be given a required the initial start of rupees 11.75, where you have to remember that y was in thousands of rupees, so it should be 11.75 thousand rupees, which is nothing but 11,750. And yeah, this is all about the question. What I want to do henceforth, using all the spreadsheet and all the questions, is have a logical intuition and also have a graphical intuition for the problem. So what I have here is actually the graph of this these points that we have. These are the 7 points. You can see the 7 blue points which are plotted, and this line is the regression line that we have found. We found y is equals to 2 plus 0.5x, and this is what the line represents. And it is very easy to see that it is indeed very close to all the points, and it looks like a good best fit line. So it looks like a good fit for the data we have. So this is kind of the graphical intuition of what we are doing mechanically over here. It's always good to have some graphical intuition. All right. Now I think we can do the next problem. Yeah, by the way, the answer for the first question here was the regression equation. This is the regression equation. And the answer for the second question is 11,750. That's what you can give for a person who has 13 years of experience. That's the end of the first question. Let's do the next question. Calculate the regression equations of x on y and y on x from the following data. So we have a data which I have also written over here, and we need to find the regression equations of both when we are regressing x on y and y on x. So if we are regressing x on y, then we need a y square, and if we are regressing y on x, then we need x square. So what I have done in the table is we have found the x square and y square values simultaneously for all the data points, because that's actually a bit convenient. So I have a x value of 10, so x square becomes 100. I have a y value of 5, so y square becomes 25. And similarly, I've done it for the all the other values. And also we need the product of the value. So I have a 10 into 5, which gives you a 50. Similarly for the all the other values. And yeah, same drill. We find the sum of all the quantities and we divide it by the number of quantities, that is 5, to get the average quantities. And then we can find the variance of both the quantities. Remember, we have to find the regression equation of both the lines. So we can find the variance of both the quantities. The variance of x is nothing but you can click here and see that it is the average of the squares minus a square of the averages. So if you have a quantity of 205.2, you subtract a 14 square, what you will be left with is 9.2. Similarly, you can find the variance of y, which is nothing but the average of the y square, and subtract from it the square of the average y. So that's what you get the variance as. You get the variance of y as 8. And covariance of xy, again, it's nothing but average of the product. This is 120 minus product of the individual averages, that is 14 and 18. So if you have 120 minus the product of 14 and 18, what you are left with is just 8. And yeah, now you need to be careful here what coefficients you are calculating. I'll denote the regression coefficient of y on x with a b sub yx, and that of x on y with a b sub xy. So that it becomes very evident that what equation we are referring to. So if we have a regression equation of y on x, then the b is nothing but the covariance divided by the variable variance of x. Because remember, when y is a function of x, x is the variable. It is the independent variable. So what you do is to calculate this, you have the covariance divided by the variance of x. You have always the variance of the quantity which is varying. So that's one way to remember it very easily. So you have a byx is equals to, you get a 8 divided by 9.2. You can simplify that or just leave it as is. And similarly, you can have the bxy. It is nothing but the covariance divided by the variance of the quantity that is varying. So in bxy, x is dependent on y. So y is the one that is varying. So you find its variance and you divide by that. So you get the variance, you get the regression coefficient of x on y as 1. And it is evident because 8 divided by 8 is 1. And again, using the average value of x and y, you can find the constant a yx and a xy similarly. So yeah, we are definitely done with the question. The regression equation for the regression equation of x on y is nothing but this x is equals to, now here a xy should come. So that's where this 6 comes from. Plus the slope, now slope is bxy, so it is 1. So it is the slope into y. So this is the regression equation of the first line. Yeah, regression equation of x on y. And similarly, you can find the regression equation of y on x, which is a yx, which is negative 4.17. Now I've rounded it to two decimal places. That's convenient. Plus the regression coefficient of 0.87. So this is 0.869. I'm rounded it to 0.87 multiplied by the variable that is x over here. So this is the final answer for this question. Also, yeah, also we can have a graphical intuition for the points. You can see that the points are plotted in blue, and yeah, you can see here that the red line denotes the regression equation of y on x. So this red line, this represents this equation, because it's the equation for y on x, and the green line represents the equation of x on y. You can see that you get two different lines, and yeah, that's even possible. You can get two different lines, regression equations. Yeah, this is kind of a good intuition. Next problem. Yeah, this one has no graph. So because we are given a bunch of data, we are not given a data points. So we are given that for a certain bivariate data on 5 pairs of observations, we are given that the sum of the x values is 20, the sum of the y values is 20. That's what we have here. So we have sum of 20, sum of y is 20, sum of the x squared values. So x squared values, the sum is 90, sum of y squared values is 90 again, and the sum of the product values is 76. And we are also given that there are 5 pairs, so I have n is equals to 5. And once we have this, we can find the averages. Just divide all the sums by 5 to get the averages. We are asked to calculate a bunch of quantities. The first one is covariance between x and y. The second one is the regression coefficient b of y on x, and the regression coefficient b of x on y. And thirdly, we have r, that is regression correlation coefficient, that's r. We will see in a moment how to calculate that. So once we have the averages of all the quantities that we require, the variance can be easily calculated. It is nothing but the, you can see carefully that it is the average of the squares minus a square of the averages. So it is 18 minus 4 squared, which is 2. That's what you get. Similarly, you can find the variance of y, which is the average of the squares minus square of the averages. That is 18 minus 4 again. Now the covariance is nothing but you can see that it is the average of the product minus product of the averages. So it is 15.2 minus 4 into 4, wherein you get a negative 0.8. And yes, you can find the regression coefficient. So yeah, this is kind of the answer for the first part of the question. We are asked to find the covariance of xy, so I can even mark this as the answer. So this is the answer for the first part. The yeah, and after we have found this, we can find the regression coefficients byx, because remember what it was. It was nothing but the covariance divided by the variance of the variable that is varying. So yeah, it might sound a bit confusing, but just the covariance divided by the variance. So here on, when you are calculating the regression coefficient b of y on x, then x is the variable. So you divide it by the variance of x. So you have a negative 0.8 divided by 2, which gives you a negative 0.4. And if you want the regression coefficient of x on y, you have the covariance divided by the variance of y, because here y is the one that is varying. So you divide it by the variance. Again, you get a 0.4. So here also I can say that this is the answer for the second question. And now comes this correlation coefficient r, and it is nothing but the geometric mean of these two quantities. When you have the two regression equations, you get two regression coefficients, and r is nothing but the geometric mean of those two quantities with the sign of those two quantities. So if the regression coefficients are negative, it will have the negative. It will, if they are both positive, then it will be positive. And the one way to do this in a spreadsheet is to have the sign of that quantity And geometric mean or the geometric average of two quantities is nothing but the square root of the product of those two quantities. So if you take the product of 0 0.4 and 0 0.4, rather negative 0 0.4 and negative 0 0.4, you get 0.16, I guess. And then if you take the square root, you get 0 0.4 back. Basically, we are taking the square root of the product of two same quantities, you will get the same quantity. But here, fortunately, we have the same quantity, which may not always be the case. So in that case, you just take the geometric mean of these two quantities to get 0 0.4, and then you put the sign of both the regression coefficients. So if both of them are negative, then you put a negative. If both of them were positive, you would put a positive. And yeah, definitely we cannot have one positive and one negative. And so if you have that, then it's a good indication that you have gone wrong somewhere. So yeah, that's what the correlation coefficient is. I can even mark that as the answer. So we have the answer to the three questions that they have asked. Next question. From the following data, estimate y when x is equals to 125. Again, very similar to what we have done earlier. But the interesting part about this question is that the quantities here are very large. So if you look carefully, the x quantities are 120, 115. So if you were to find the square of these values, they would become a bit cumbersome. Now I know if doing it in a spreadsheet, it is easy, but if you were to do it by hand, then finding the squares of these quantities is a bit hard. So what you can do in this case is you can shift the points, and then that shift will be taken care of by itself when we do the further calculations. But what we have done over here is that I have shifted my x points by a suitable quantity, that is 115, because if I look carefully, that the minimum of my quantities, x quantities, is 115. So if I remove 115 from each quantity, what I get is these values of u. So I have defined u as, you can even see from here, it is nothing but the original x quantity minus this shift of x. So I have a 120 minus 115, it gives me a 5. If I have a x is equals to 115, subtracting 115 from it will give you a 0. And you can check, let's say for this example, you have a point of 126. If you subtract 115 from it, you get 11. And similarly for all the other quantities. So you can shift the x values by 115 to get u values. And yeah, again, you can see that these values, they are very close enough, but they are still large. So doing the calculations with these points is a bit difficult. So what you can do is you can again shift it by a suitable quantity. I've chosen y. A shift in y is 12. So you can have a 13 minus this shift, will give you a new value. Let's call it v, which gives you a 1. And 15 minus 12 gives you a 3. 14 minus 12 gives you a 2, and so on for all the other values. So what you have is you have converted your xy problem into a uv problem where u and v are small. So these are numbers which are easy to calculate with, especially when you are doing by hand. So if you were to forget about the xy values and just focus on uv values, your problem now reduces to finding the regression coefficient with these values, which are easy to do. What you do is you find the square of the u values, because again, remember, x was the independent variable, y was the dependent variable. So when you shift it, u becomes the independent variable, v becomes the dependent variable. So you find the square of the u values. These are the square numbers. And now you realize that finding squares of these small numbers is easy compared to finding squares of these large numbers. That's the benefit of shifting the values. So it's basically shifting the origin, but yeah, the calculations become a lot easier. That's the whole point. And you can also calculate the product uv to have very good small numbers. These are the product values. And the same drill, what you do is you find the sum of all the quantities and you find the average of those quantities. And then you can find the variance of the variable. Now here the variable is u, because earlier the variable was x. So when you have transformed x to u, your variable becomes u. So you find its variance, and it is again nothing but the average of the square values. Obviously the square of u, not x, because that's not what we have calculated. We calculated the squares of u. So you find the average of u square, and you subtract the square of the average of u. So you have this value, you subtract square of 6.5, you get these values. And of course, when you're doing it by hand, it's I think better to leave it as fractions. So, but these are the values that you get, and you can also calculate the covariance between u and v. Again, the same drill. It is the average of the products minus the product of the averages. So it's what you get. You get a value of negative 2.91 something. And now you can find the regression coefficient of v on u, because remember we wanted regression of y on x, because x was independent, y was dependent, and since we shifted xy to uv, now here we want the regression coefficient of v on u. So that's why I've calculated the regression coefficient of v on u using obviously the covariance and the variance. So it is nothing but the covariance divided by the variance. So and yeah, this is what you get, whatever that number is. I don't care about the numbers. But the crux of this question is that you can use this same regression coefficient as the regression coefficient of yx, because remember what the regression coefficient is. It is nothing but the slope of the line. So when you are shifting, the slope of the line doesn't change, because you are just shifting the line somewhere. It's basically shifting the origin. That doesn't change the slope. In case you were scaling the points, yes, then that would change the regression coefficient, but just shifting wouldn't change the slope of the line. So you can use the same regression coefficient as the regression coefficient of y on x. So what I've done is I've actually used the same thing here. So you can see the regression coefficient of y on x is nothing but the regression coefficient of v on u. And now that we have the regression coefficient of y on x, I can again use my original average values of x and y to find the constant ayx, which is nothing but the y average minus the b that I've calculated into the average x. So yes, that's what it's supposed to do. And we have actually the regression equation of y on x. It is nothing but this a plus b, this b into x. So yeah, actually the question asked is asking us to find y when x is 125. So we have a sample x of 125, and using these a and b, we can predict that y comes out to be this. So it is again, if you want, you can check that it is a plus b into x. So that's what you get the value as. The predicted value of y is 12.75 something. So your answer is this. And again, this is what I was emphasizing on when you are shifting the points. But yeah, you can also have a graphical intuition for this problem. These are actually the original xy values. These are not the uv values, uh, or are they? Yes, these are actually the xy values, and this is the line regression line of y on x. So that's what I have calculated using the regression coefficient b and this constant a. And you can even eyeball from this line that if you have a sample x of 125, it will lie somewhere between 124 and 126. And if you were to look at up that line, you can estimate that the predicted y value will be around 12.7, so around somewhere here, makes a lot of sense, because the value that you got was 12.75. So it has a logical, it has a graphical intuition as well. This is the graphical intuition. So yeah, if I were to emphasize my answer would be this. This is the y value for x is equals to 125. Next question. Following table gives the aptitude test scores and productivity indices of 10 workers selected at random. So we have aptitude scores denoted by X, and productivity index denoted by Y, which I have tabulated over here. And we are asked to obtain the two regression equations and estimate the productivity index of a worker whose test score is 95. So in this first problem, test score is 95. So we are given that x value is 95. We are asked to predict the productivity index. So we are asked to predict y when x is 95. So for this question, we'll require the regression equation of y on x. And for the next part, the test score when productivity index is 75. So in this one, we are given the productivity index, we are given y, and we are asked to calculate this aptitude score. So we are given y, we need to find x. So in this question, we'll require the regression equation of x on y. And yeah, that's what we are supposed to do in this question. But again, the very first thing that you realize that these numbers, they are large enough, but they are close. They are close by. So if you have a shift of 65 in the x direction and 62 in the y direction, you can see that your uv values become small, which are easy to calculate with. So these are the uv values that you get. Feel free to pause the video and check that these are the values that you get, and then you can do the same drill. You can find u square values, you can find v square values, you can find the product, you can find their averages, and then you can find the variance of u, variance of v, and covariance of uv. And you can, since we want the both the regression equations of y on x as well as on x on y, we find both the regression coefficient. We find the regression coefficient of v on u as well as u on v, and these are the regression coefficients that you get. Feel free to just check the numbers. And again, the master stroke is that using the regression coefficients of v on u as the same as the regression coefficient of y on x, because shifting has no effect on the slope of the line. So you can use these same values as your regression coefficients for x and y. And once you have the regression coefficients, you can obviously calculate the constant a using the average of x and y that you got. So these are the constants that you get for two regression lines. And yes, for the first the regression equation, first of all, the regression, we are asked to find the regression equation. So the regression equation of y on x is nothing but y is equals to now a y x. So a y x is negative 10.9 something. So we have a constant of negative 10.9 plus b into x. Now b here is b y x. So it's 1.167. So I have rounded off to two decimal places. It's 1.17x. And the regression equation of x on y is x is equals to a. Now here a will be axy because x is dependent on y. So we have axy, which is 26.27 somethings, and plus b value of bxy, which is 0.6 something. We have rounded it to one decimal place, 0.6y. So this is the regression equation, the two regression equations, and you can use the first one to find the value of y when you are given a sample x value of 95, because remember the sample value in the first question was the test score, which is x equal to 95. So we have a sample of 95, and using the first equation, this value of test value of productivity index y, it comes out to be 100 point something. So you can have a productivity index of 100 when you have a test score of 95. And similarly, you can use the other equation because here x is dependent on y. So when you have a sample y of 75, you can predict that x is equals to 70 point something using the second equation. So yeah, this is my final result. If a test score is 95, your productivity index is 100 point something. And if your productivity index is 75, your test score is 70 point something. Also, we have obviously the graphical intuition for these points. What we have here, these are the xy values being plotted in blue, and you can see that the red line is the regression line of a y on x, and the green line is the regression line of x on y. They're pretty close to each other. They're also pretty close to the points in the picture. So yeah, this is graphical intuition also. But yeah, this is the final answer. Next question. Compute the appropriate regression equation for the following data. We are given x values and y values, and here we are told that x is the independent variable and y is the dependent variable. And yeah, of course, there's a typo. This should be a var. This should be a var, but just forget about that. The important point here is that y is dependent on x. So what we require is the regression equation of y on x. And yes, again, if you want, you can shift the points, but I believe that these numbers are small enough, so there's no need to shift the points. I can just use these points. You can see that I've calculated the square of the x values. remember that you have to find the square of the independent variable. So if you have a 2, you square it to get a 4, and so on for all the values. And also you want to find the product of the two variables, that is x into y, and then you find the average of all the quantities, which will help you in finding the variance of the variable, that is x, the covariance between the two quantities. And when you take the ratio of these two, you get the regression coefficient b. So you have a covariance divided by the variance to give you a regression coefficient of negative 1.34. You can check the numbers yourself, and once you have the regression coefficient, you can use the average values and the regression coefficient to find the constant a value. So you have the regression equation as y is equals to a, which is 18.04, plus b into x. Now obviously b is negative, so I would have a negative 1.34x. So this is pretty simple. Also, the graph looks something like this, where you have the points. The points are plotted in blue, and this equation y is equals to 18.04 minus 1.34x. This is the line that it represents, and it's very clear that it is a best fit. It is a good fit for the points that we have. Next question. Following are the marks obtained by the students in economics and mathematics. X and Y are X is the marks of economics, and Y corresponds to mathematics. Here has to find the regression equation of Y on X. Again, same drill. Uh, but one thing again, you realize that the numbers are very big, which are a bit cumbersome to calculate. So we shift them because they're also close enough. So if we shift them, they will become small. So what I've done is I've shifted the x values by 61, because what you realize is the minimum x is 59, the maximum is 63. So if you shift it by 61, which is kind of in the middle of those two, the values of u that you get are these, which are very small, and these are easy to compute with. And similarly, if you shift the y values by, let's say, 80, then v values that you get when you subtract 80 from all y values are these v values that you get, which are again very small, which are very small, which are easy to compute. So you consider this as a new problem. You have a u and v values, for which you find u square again, and the product u into v. Also, you find the averages of all the values, and then you calculate the variance of the variable. Now here, since we wanted regression of y on x, our shifted problem will have a regression of v on u. So here u is the independent variable, so we find the variance of that variable, which you can check that it comes out to be 2. The covariance between u and v comes out to be 0.6. And then you can find the regression coefficient of v on u, which is nothing but the ratio of the covariance and the variance, which comes out to be 0.3. And use that as the same regression coefficient for y on x, because again, remember, shifting does not have any effect on the slope of the line. So if you shift by some amount in any of the directions, the slope will remain same, and therefore the regression coefficient will remain the same. So you can use the same coefficient, and once you have the slope, you can again use the average values to find the constant a. So the regression equation that you have is y is equals to the constant, which is 62.1, plus the regression coefficient 0.3 into x. So this is the final equation that is required. And also you can see that the points are plotted in blue. They are a bit far away, but the regression line that we have found goes through kind of in the middle of all the points. So it is kind of a good fit for the points that we have. Next question. For the following bivariate data, obtain the equations of two regression lines. So we are given x values and y values, and we're asked to find the regression equation of x on y as well as on y on x. So yes, again, the values here are small, so I wouldn't bother shifting the values. So I can directly calculate the square of the x values, square of the y values, and the product of the values to get the average of all the values, which can be used to find the variance of x, variance of y similarly, and the covariance as well, which can be used in turn to find the regression coefficient of y on x, which is nothing but the ratio of the covariance and the variance of the independent variable. The independent variable is x, so we find its variance and divide by that variance. And the regression coefficient of x on y is the covariance divided by variance of y, because here y is the independent variable. So you have a 4 divided by 8 to give you a 0.5, or half basically. And once you have those, you can simply calculate the constant a, which is nothing but what you get when you have x and the average x and average y passing through the line, and these as the slope. So this is pretty similar to what we have been doing for the past few problems. And the regression equation of x on y is the a constant constant a xy, which is negative 1.5, which is what we got here, plus regression coefficient b, which is bxy 0.5 into the variable y. And similarly, the regression equation of y on x is y is equals to the constant 3 plus the regression coefficient of y on x, which is byx, which we found out to be 2 into the variable x. So this is the final answer. If you want a graphical intuition, you can clearly see, and in fact, it's such a beautiful graph that if you plot the points, points are in blue. The regression equation of y on x and x on y, the red line and the green line, they are coincident. In fact, they are on the same line. Also, all the points pass through that same line. And this is beautiful because if you look carefully, these two are the same equations. If this is kind of a multiple of the second equation is kind of first equation multiplied by 2. You can check the calculations. It's twice the first equation is the second equation. But the major beautiful thing here is that all the points satisfy both of these equations. So that's why the all the points, they lie on both the lines. So that's kind of the graphical intuition for this problem. So it's very beautiful that the best fit line passes through all the points that we have. But yeah, if you were to find the final answer, this is your final answer. Next question. From the following data, obtain the equation of two regression lines. Again, very similar to what we did earlier. We have a bunch of data points. I did not mind shifting the points because these are close enough. You can do all of the drills, find the square values, find the square values, find the product values, and then the averages, find the variance of two values and covariance. It's kind of becoming very repetitive now. So yes, the final result that you get is this. You can check the numbers that you get. Again, the graph that you get is this. You have the points plotted in blue. The red line is the regression of y on x, and the green line is the regression of x on y. This looks like a good fit. But yeah, this is kind of the final answer. You can feel free to just check the numbers. Next question. For the following data, find the regression line of y on x. We are given the data, this is just 3 data points, and hence find the most likely value of y when x is equals to 4. So once we have the line y is equals to a plus bx, we can put x is equals to 4 in that and find the value of y. So that's what we have done. Again, I don't bother shifting the values because they are very small and easy to compute with. So after doing all of the same drill, the same steps, finding variance, covariance, the regression coefficient, and the constant, this is the equation that you get. And for a sample value of x is equals to 4, you can see that the predicted value using this equation, it comes out to be 7. So if x is equals to 4, y is equals to 7. And you can also check it from the graph. If you plot the 3 lines, the 3 points, sorry, and the regression equation, or rather the regression line that you get, this is the red line that you get. And if I have a x value of 4, so that's x value somewhere here, if you project it on the line, the y value, you can see that it comes out to be 7. So yes, that's kind of good enough. So yes, if x is 4, y is 7. So that's what your final answer is. If you want the regression equation, this is it. Next question. From the following data, find the regression equation of y on x and estimate y when x is equals to 10. Very, in fact, almost the same problem, just different data points. You have the data points, 6 data points. You have found the variance, covariance, and the regression equation. which is equals to y is equals to 2.8 plus 0.63x. And if we plug in a sample value of x is equals to 10, the outcome of y that you get is 9.1 something. So this is your final answer. You can even see from the graph that the blue points are the points that we are given. The red line is the regression line. And if I were to look at it at the x value of 10, now I don't have the graph plotted at 10, but if you can extrapolate it to 10, you can see that it is somewhere near 9. The y value is somewhere near 9. So this makes sense. A y value of 9.1 makes sense. So yeah, next problem. The following sample gives the number of hours of study X per day for an examination and marks obtained by 12 students. So we have a bunch of values. So the first value represents a person who is studying 3 hours a day, and he or she scores a 245 marks. And similarly for all the other points, we need to obtain the line of regression of marks on hours of study. So marks are represented by Y and hours of study by X. So we need the regression of Y on X. And again, the same drill. What you can do is you can have the X values and Y values. But again, one thing you realize that the values of Y, they are very large. And so it might be a bit difficult to do the calculations. So we have shifted the values. So we have shifted X value by 5. So we have subtracted 5 from each value to get U values, and we have subtracted 70 from all the y values to get a smaller v value. So these are comparatively smaller. These are easy to compute with, and using these data points, we have found the u square values, the product values, the averages of all quantities, the variance of u, the covariance of uv, and the regression coefficient of v on u, which can be used as the regression coefficient of y on x. Because again, remember that slope has no effect, or rather shifting doesn't have any effect on the slope. So we can use the same slope that you got for your original data points. And once you have the slope, you can use the average values to find the constant a. So you have the required regression equation as this. It's y is equals to a, which is 38.39 something, plus a b value of 6.6 somethings into x. And you see very clearly from the graph here that the blue points represent the data points, the 12 data points that you have, and the red line is the regression line of y on x, which is it's kind of good to see that it is very close to all the points that you have. But yeah, if you were to find the final answer, this is your final answer, and we are done with the problems.